Right, good afternoon, everybody. So in last class, we were talking about dynamic memory management. And we were looking at this function called realloc. So realloc is the function that you use if you have a block of dynamically allocated memory and you want to change the size of that block of memory. So typically you want to make it bigger, but you can also make it smaller. So remember, so the way you call the function is you pass in the pointer to your memory that you've previously allocated before, and then you ask for the new size of memory that you want. Right? And again, remember, new size is always measured in terms of the number of bytes or the size of car. If the function succeeds, then you end up with a new block of, well, you don't necessarily end up with a new block of memory. You end up with a block of memory that holds the contents that used to be in the previously allocated block of memory. If the new block of memory is bigger than the previously allocated block, then everything else, then the excess memory is not initialized to any particular value. If the new block of memory is smaller than the previous block of memory, then any of the, then you're going to lose some of the elements that used to be in the previously allocated block of memory. Right, because you've shrunk the amount of memory that's there. Let's see, so there's, okay, so here's an example of using realloc. So we're going to make an array here using malloc, right? Now to use realloc, you have to either call malloc or calloc first. So you need an allocated block of memory. So here make array is going to allocate a block of memory. And then we're going to ask the user again, what is the new size of memory that you want, and then we're going to call realloc on that new block of memory. So notice when you call realloc, you pass in the pointer to the pointer that was returned by malloc, back up here, right? So our pointer is ARR. In this case, ARR is just an array of int. Right? When you ask for the new size, it's always the number of elements times the size of whatever it is you want to put, times the size of the element type that you want to store in the new block of memory, right? And you can make it bigger or smaller, right? And when you run this program, hopefully this is the right version. Okay, so if you make an array of size 10, right, you end up with an array of size 10, and our code initializes it so it has the values 0 through 9. If you want to make it bigger, let's make it 19, right? You end up with a new array that's bigger than the old array, right? So it now has size 19. The elements of the old array are all still here, right? And then you have an extra 10 elements over here, assuming I did my, sorry, an extra 9 elements over here, right? And notice that the memory is not initialized for you. So we have this funny number here, 132385, right? And that's because the newly allocated memory just has a bunch of random bits in it. And so when they're reinterpreted as ints, you get some funny value. Right, so realloc does not do any initialization for you. If we make the array smaller, so we'll make an array of size 19, and then we'll make an array of size 2, right? You end up with all the existing elements, all of the previously existing elements that still fit into the new array. Right, so here we only have space for 2 elements. Okay, so before I talk about structures, I want to talk about this thing called typedef. So a typedef declaration lets you make up a new name that corresponds to an existing type. Right? So it provides a way to declare what's called an alias that can be used to replace a possibly complex type name. So in C, it's possible when using pointers, and especially pointers to functions, that your types can become very, very long and very complicated to read. So instead of having to repeatedly type in a very long type name or to repeatedly try to reinterpret a complex type name, you can use a typedef to give it a much simpler name. Right? Now, when you use a typedef, you're just introducing a new name. You're not actually introducing a new type. Right? So the way it works is you use the keyword typedef. Then you put in the existing type, and then you put in its new name that you want to use for the existing type. And then there should be a semicolon at the end here, but it's not shown on the slide. Right. So for example, type defs are used throughout the standard library in several places. Although they don't necessarily have to be, but they are at least on my machine. So this type size t, right, that we've been using in the course. Remember, size t is the is the type that you would use to store the size of an object in C, right? And it's guaranteed to be able to store the size of the largest possible object in C, right? It's unsigned because it corresponds to a size, right? Its actual type on my machine anyway is long unsigned int, right? So there's our type. Right, now instead of writing long unsigned int everywhere, we can just write size t. Right? But size t, again, is not a new type. Right? It's just a new name for an existing type. Right? There's a type called pointer difference type, or pointer difference underscore t. Right? So if you take two pointers and subtract their values, then the type of that result is stored in a long int. Right? So pointer difference underscore t is just another name for long int. Right? And occasionally you'll see this type in some of the standard library functions as well. Right? And there's many other examples that you could find. Right? Now, of course, you can use typedef to make your own names for possibly inconvenient types. Right? So if you wanted to, so there's a pointer to an int, right? So that's my type, so int star. Right? If I wanted to make a typedef for that, I could call it int pointer underscore t. Right? So instead of having to remember that int star is a pointer to an int, you can just use the name int underscore pointer underscore t, which probably is harder to write. So this is not a good example of a typedef. Right? But at least you can read it and not have to think that, oh, this is a pointer to an int. What typically happens is that typedefs are very common when you start to work with pointers to functions, which is what we're going to do, I think, in the next lecture or the lecture after that. Right? And so it turns out that in C, you can have a pointer to a function, and you can store that in a variable. So the problem is you need a variable whose type is the pointer to your particular function. Turns out to be very powerful because this means you can pass pointers to functions around in the C language. So if that means you can store a function in a variable and pass that to another function for that function to use. And this is what lets us do genericity in C. Right. Okay, so this very complicated looking type here I'll just decipher this for you. So the way this particular typedef looks weird. So it turns out f underscore pointer underscore t, that's our new name. So it's a bit weird when you work with pointers to functions. Right? So that's our alias right there, f underscore pointer underscore t. The type of the function is the following. So the function that this thing points at returns an int and takes in two ints as its parameters. Right? So f ptr underscore t is able to store a pointer that points to a function that returns an int and has two ints as its parameters. We're going to look at this in more detail in a lecture a couple days from now. Right, so this is just introducing the use of typedef. C is also strange in that you can have what are called incomplete types. So in C, there's the declaration of a type, and then there's the definition of a type. So on the next line here, I have a declaration of a type, but I don't have a definition of a type. So the next typedef says there's going to be some structure, which I'll talk about in a second, called list. And I'm going to just say, I'm going to make an alias to that type as just list. Right? So in other words, instead of writing struct list everywhere, I can just write list instead. Right? I don't actually know what this is yet, so I haven't actually defined what struct list is. So in this case, struct list is what's called an incomplete type. Right? I've declared that it exists, but I haven't defined what exactly it is yet. We're going to see that in the next lecture. So if you really wanted to use one of these typedefs, so for example, let's use our pointer to an int, right? Then in make array returns a pointer to an int, right? So it returns, it allocates an array. So instead of storing, instead of declaring array as being an int star variable, right, or a pointer to an int, I can now use int underscore pointer underscore t instead. So this is just a substitute for the actual type int star, right? That's all it is. And then the rest of the program works the way, so when you make an array, you can actually store the result in a variable whose type is now int underscore pointer underscore type, right? But again, really that's just int star. Right. All right, so let's look at a slightly more useful example of a pointer, of a type def. And to do that, I'm going to introduce this thing called a structure in C. So a structure in C is what's called a composite type. In other words, it's a type that's made up of other types. So the easiest way to think about a structure in C is to think of it as a Java class that has some public fields, and that's it. Right? So it's just a class that has some public fields, or corresponds to a Java class that has only public fields. Right? So just like a Java class, right, a structure lets you group a bunch of variables into under a single name, right? And in C, they actually get grouped into a single block of memory. Right? So just like a Java class that has a bunch of fields, right? All of those fields are grouped into a single class. Right? So in C, you can group a bunch of different variables into a single struct or structure. Right? The syntax is pretty close to Java as well. Instead of class, you use struct. Right? You give the structure a name, and so in this case it's called a tag, but that's not really important for our purposes. Right? Then there's some braces and a semicolon. Right? And then your variables that you can have in your structure just are just listed one after the other. Right? So that's a variable type, and that's a variable name, that's a variable type, that's a variable name, and so on, and so on, and so forth. So for example, if you wanted a structure that can represent a two-dimensional point having real coordinates x and y, you could declare it as follows. Right? So struct point 2. Struct point 2 becomes the actual type name. Right? So struct point 2 introduces a new type. Its type name is struct point 2. So you have to keep on writing the struct. Right? What's inside of a struct point 2 object? Well, there's a variable called x whose type is double, and there's a variable called y whose type is double. Okay. To use this thing, you just declare a variable of type struct point 2. Right? So I have a variable called p. Right? P now has a member called x and a member called y. Right? And you get to the members the exact same way you would get to a field belonging to an object in Java. Right? You use the dot operator to access the members. Right? So px is the x variable that belongs to p, and py is the y variable that belongs to p. Right? There's no constructors or anything like that in C. Right? So when you make an object of type p, sorry, the volume's a little loud. When you make an object of type p, what happens is you get a chunk of memory. That chunk of memory has a double in it, has two doubles in it. One is labeled x and one is labeled y. Right? You can have as many of these members as you want. Right? So and the types don't matter. So you could have another int, you could have a pointer to a car for a string, and so on and so on and so forth. Right? So you can have as many members as you like. If you create, sorry, do I have to? No. All right, so in this case here, if you print out that, when you actually print out px and py, in principle, you can get anything. Because here, we didn't initialize the structure object. Right? We simply said p is a structure object. In C, you get some random chunk of memory that's got space for two doubles in it. And so the values there could be anything. If you actually ran this program, I'm pretty sure you'd get 0 and 0, because the program's so short. Okay, so structures are a bit weird. So when you declare a structure, the structure has what's called a tag name. Right? The tag name is not the name of the type. The name of the type is struct followed by the tag name. The tags, or the tag names, they exist in what's called a different namespace. than identifiers such as variables, type-def names, and function names. Right? And so what that means is that the location for the tag, it's not the location. The way that the language manages the tag names is separate from how it manages all other names. Right? And so that means they don't overlap. So you can have a tag name and a variable type name, or a variable whose names are the same. Right? So in other words, I can think of, so back here, sorry. So in other words, one type is struct point 2, but if I wanted to, I can declare another type using typedef that's also point 2. Right? And so there's no clash, there's no overlap in this case. Right? So what many programmers will do, instead of writing struct followed by the tag name everywhere, is that they'll just create a typedef. So for example, oh wait, here, right? That's the same example as the previous slide. Okay, so here's my struct again, right? And then what you can do right away is you can do a typedef, right? And I can write struct point 2, right? So there's my type, and then I can write point 2, right? So instead of writing struct point 2 everywhere, I can now write point 2 instead, right? And the reason this works is because the typedef names, like point 2, right, are maintained in a different way than the structure tag names, right? So there's no overlap of the name point 2 in this case, right? Now I can just write point 2p, right? And that's exactly the same as if I had written struct point 2 instead, right? So many programmers will do this. Many other programmers will tell you you should not do this. So in particular, the people who write the Linux kernel say you should not do this. You should write struct everywhere because this doesn't really save you. Number one, it doesn't save you a lot of work. It just prevents you from having to write struct. And number two is it now clutters your program with more type names. So the Linux kernel people don't like it, but many other programmers will do it. All right, so if you have a structure, can you initialize the members of the structure? The answer is yes. So C has a special notation for initializing the members of a structure. It looks exactly like the way you would initialize an array, right? So you put some braces down, and then inside the braces, you can put the values for the individual members of your structure, right? You separate them with commas. If you want to, you can even specify the name of the member that you want to initialize, right? And the way you do it is a bit funny. It's easier to see an example. But the way you do it is you put a dot in front of the member name, and then you put an equal sign. So let me just show you how that works in a second. Okay, so right here. So here's my structure again, right? It has an x and a y coordinate. So to initialize p to 2 and 3, I can use braces, right? It's exactly the same as if you'd initialize an array. And then I can specify 2.0 and 3.0, right? So in this case, the 2.0 gets assigned to the x, and the 3.0 gets assigned to the y. So if you print out that point, you'll get 2.0, comma 3.0. If you want to say which value goes to which member, you can specify the name by writing dot and then the name of the member. So dot x equals 1 assigns 1 to x, and dot y equals 1.5 assigns 1.5 to y. Right? I guess more precisely, it goes to qx and qy. So when you print qx and qy here, you'll get 1.0 and 1.5. You don't have to explicitly initialize all of the members. So here, I can write dot y equals minus 3.1. So when you print out the point, ry will be minus 3.1. Anything that you don't explicitly initialize gets the value of 0. Right? But only if you attempt to actually initialize it. Right? So here I'm actually trying to initialize the structure. So Rx will get assigned the value 0. Right? If you don't initialize the structure like this, right? So here it's just 0.2p, then the members are not initialized. Yeah, the members are not initialized. So you could get any, you could have any values for px and py in this case. Oh, I guess we should just run this. So struct point 2 underscore 2. Like that, right? So you get p is 2 and 3, q is 1 and 1.5, and you can see with r, we didn't initialize x explicitly, but it is in fact the value 0. And the language guarantees it'll be the value 0. Okay, so if you have a structure object, you can access the members using dot, right? So variable name dot member name, that gives you the value, or that gives you access to that member. If you have a pointer to a structure object, right, then instead of using dot, you can use hyphen greater than, so the arrow operator. Right? And so the arrow operator, remember you have a pointer to a structure, the arrow operator dereferences the structure, dereferences the pointer to give you the object that the pointer is pointing at, and then it lets you access the variable name or the member name. Do I do it both ways? Hopefully I do it both ways. Oh wait, yeah I do, okay. So here's p, right? I'm going to initialize it to 2, 3. Down here I've got a pointer to a point 2 object, right? I'm going to assign it the address of p, right? So in other words, pointer points at p. Right? Now to change the x and y coordinates of the point, I can use the pointer instead, right? So I can write pointer arrow x equals 200, right? So that dereferences the pointer to give me p, then gives me access to the x field member, sorry, which I can set to 200. Right? And then pointer arrow y, right? That dereferences the pointer to give me the p object, right? Then it gives me access to the y member. So py is now 300, right? And when you print out px and py, you'll get 200 and 300. Sorry, just let me quickly check the next slide to see if, okay, so I should show, there's another way to do this as well. So if we run this, right, you can see that p changes to 200 and 300. So let me just pull, oh wait, I have it up. You don't have to use the arrow operator. You can always just dereference the pointer yourself. Right? So here I'm using the arrow operator. Right? If I wanted to instead, right, there's nothing from stopping you from dereferencing the pointer yourself. Right? So if you dereference the pointer, that gives you the object p. Right? Now I can use the dot operator to access x and y. Like that. And then if I print the point, like that. And then if we recompile the program, right, and you can see that it also, it does in fact change the coordinates of px and py. Right, so you don't have to use the arrow operator if you have a pointer. You can always dereference the pointer manually yourself. You just have to remember that when you do that, you have to wrap up the dereferenced pointer using round brackets in order to use the dot operator. The reason you need to do this is because the dot operator has higher precedence than the dereference operator. Right, so if you leave the brackets off, right, it tries to access the x member of PTR, which doesn't exist because PTR is a pointer. Right, and then it tries to dereference that value. So that doesn't work. You have to wrap up the pointer. You have to wrap up the pointer in round brackets and then dereference the pointer. Okay, so structures, you can, if you have a structure object, you can assign it to another structure object. And what ends up happening is all the members get copied member by member to the assigned to object. Right. Now, if the structure contains a pointer, right, then what happens is that the value that's stored in the pointer gets copied over into the other pointer. Right? And so remember that the pointer stores the memory address of an object. Right? And so now you have two pointers that point to the same object. right? You don't get a copy of the underlying object that the pointer is pointing at. So you have to be a little bit careful when you do that. So here's P, right? It's 2, 3. Here's Q, which is uninitialized, right? So when you print it out, you could get anything, but you probably get 0 and 0. If you write Q equals P, right, what the compiler literally does, well, not what it literally does, what the compiler effectively does is it ends up writing Qx equals Px and Qy equals Py, right? So each member gets copied individually. How it actually happens, who knows? You'd have to look at how your compiler is implemented. If you change Qx and Qy, right, P doesn't change, right? So, okay, so Q and P, they really are separate point 2 objects, right? When you write Q equals P, they're still separate point 2 objects, right? Qx is not the same as, Qx is not the same variable as Px. Qy is not the same variable as Py. So if you change Qx and Qy, Px and Py does not change, right? So here we should get 2, 3, something, something, 2, 3, 2, 3, and then 200, 300. And we do, right? So P starts out as 2, 3. It looks like Q is starting out as 0, 0, right? When we assign Q at P to Q, Q also becomes 2, 3, right? P is still 2, 3. And then if we change, after changing the coordinates of Q, Q becomes 200 and 300, right? And P doesn't change. You can dynamically allocate a structure, right? Or an array of structures if you like, right? How do you do it? Well, you just use size of to get the size of the structure. So here I am allocating, using malloc, space for exactly one 0.2 object, right? So size of 0.2 is the size of one of these, one structure object, right? So in this case, it should be the size of 2 doubles, right? Because that's what a structure is made out of, right? P actually points at a 0.2 object after you do this, right? So malloc allocates enough space for that object, right? Does not initialize the memory. I can then use the pointer and the arrow operator to set the X member. I can use the pointer and the arrow operator to set the Y member, and then print out P, and that should be 200, 100 and 200. And it is. So what else can you do with structures? Well, it turns out you can't do a whole lot else with them directly, right? So for example, if you wanted to test, are two structures equal? You can't do it. So if you try to use equals equals or not equals for structure variables, the compiler will end up complaining. It'll say that those operators are not defined for structs. Right? And so there's no built-in test for equality. And one of the reasons there isn't is because it's not clear what it means for two structures to be equal. Right? So if you need to do this sort of thing, and you might want to do this sort of thing, especially for point objects, right? It kind of makes sense that you want to test if 2 points are equal. If you need to do this sort of thing, then the correct way to do this is to write a function, right? Especially if you need to do this more than once, right? So first of all, you have to decide what does it mean for two structure objects to be equal, right? And then once you've decided what it means, you go ahead and compare the relevant members. So here I'm not going to write a function for it. Instead, I'm going to do it manually. Right? So here I've got a pointer to a structure P. Right? The point has coordinates 100 and 200. Right? I'm just going to make a plain old structure Q. Right? I'm going to set it to also 100 and 200. Right? I now want to know, is the object pointed at by P equal to the object Q? Right? And here I'm going to say they're equal if they have the same coordinates. Right? So how do you test if they have the same coordinates? Well, I need to get the X coordinate of P. Right? So either star P round bracket dot X or P arrow X. Right? Is that equal to QX? right? And is the y coordinate of P equal to QY? Right? If they are, I'm going to print they have the same coordinates. Right? And this should print they have the same coordinates. Right? So star P and Q objects have the same coordinates. Right? Obviously, if you change QX or QY or PX or PY, that's no longer going to be the case. Okay, so as soon as you start to make a structure, usually when you're making structures, you're often making some kind of data type. And then when you have a data type, it's natural that you're going to have functions that operate on that data type. So at this point, you now have to think about how are you going to organize your code. And so that leads us to the organization of a C program, which I've talked about a little bit already. Right? So when you make a type like point2, it's often the case that you want some functions that operate on point2 objects. Right? In Java or in any other object-oriented programming language, right, you would create a class. Right? The class would have the fields of the structure, and you would have methods inside the class. Right? In an object-oriented programming language, you might also create a utility class, so a separate class that can also operate on, in this case, point2 objects. Right? So there's nothing stopping you from doing that. So the way it works in C is what you would typically do is you would place the point2 structure and all of the function declarations that you want to operate on those on that structure into a header file. Right? So remember, header files by convention have the extension .h. Right? And then you would place the definition of the functions into a separate C source code file. Right? So in other words, for this point2 thing, I would create two files. Right? Point2.h would be the header file, and point2.c would be the C source code file where the functions that operate on point2 objects are defined. Right? And so I'm going to cook up just a bunch of point2 functions. Right? So move is going to move a point. When it moves the point, it's going to change the x and y coordinates of the point. Right? So it's going to move it by dx and dy. Right? Now, if I'm going to change the coordinates of a point object, I need a pointer to that object. Right? I can't just pass in a regular point2. I can't not pass in a pointer. Right? If I don't pass in a pointer, right, then I end up, if I change the values, the coordinates of P, the caller is not going to see changed values. Right? Because C uses pass by value, so when the caller passes in a structure, the structure gets passed by value. Right? So in other words, you get P is a copy of the object that gets passed in. Right? So I need to pass in a pointer instead. Multiply is going to multiply the coordinates of a point by S. Right? Again, if I'm going to change the coordinates to that point, I have to pass in a pointer to that point. Equals is going to test are 2 points equal. Right? Now here I don't need to pass in a pointer. Right? So I can just pass in a plain old point instead. Right? If you wanted to, you could also pass in a pointer. There's nothing wrong with that. These are marked as const. Right? Now in this case, that doesn't actually do anything. So all this says is that the function here is not going to change the coordinates of P or Q. But it doesn't matter if it does change the coordinates of P or Q. The caller is not going to see the changed coordinates anyway. Right? So the const here doesn't actually bias anything. Neither does the const here. Right? You would only really want to put const in if these were pointers. Right? Because that guarantees, that says that the function is not going to change the caller's point2 object. Notice that when you do this sort of thing, typically what ends up happening is the type name gets appended to the front of the function name. Right? So point2 underscore move instead of just move. Right? Point2 underscore mult instead of just mult. Right? The reason this is typically done in C is because C function names have to be unique across all compilation units. Right? So in other words, if I just call this move, or if I just, sorry. Go away. Sorry. If I just call this move, or mult, or equals, or toString, there is a good chance that somebody else, or somewhere else in the program, there's also another function called move mult equals or to string. Now the names clash and the program won't link. Right? So it's very common that you end up appending the name of the type in front. Right? And hopefully that reduces the probability that you end up with clashing names. We've briefly talked about this already, right? But when you make a header file, the header file should always include what's called a header guard. Right? And the reason you include a header guard is because you don't want the declarations to be included more than once into any C source code file. Because then you have two declarations of the same thing, and sometimes that's a problem. Include guards are typically implemented using what's preprocessor directives, and they typically look like that. Right? So for my point2 object, I'm going to create a header file called point2.h. Right? The first thing that you do when you make your header file is you automatically stick in your header guard. Right? So if the name point2_h is not defined, right, then the stuff inside up to end if will happen. Right? So everything else will actually, the preprocessor will, in other words, the preprocessor will process everything between if end def and end if. Right? So the first time point2.h gets included into the program, that name is not defined, so we'll define it. Right? The rest of the header file gets included, and then we hit the end of the header file. Right? If someone tries to include the header file a second time, right, point2_h is defined according to the preprocessor, right? And so everything else in here gets skipped. So that prevents the header file from being included more than once into your program. Right? Now you go ahead and you put in your structure. Right? So there's our point2 struct. If you want to, you can have a type def. Right? And we declare our functions here. Right? Now anybody who wants to use our point2 object can just include this header file. And that's it. Right? So they include the header file. When they compile the program, they link to our point2, to our compiled point2.c file, and now they can use the point2 object in their programs. Right. So where do the function definitions go? Well, they go into a separate C source code file. Right. So now we make point2.c, right? And the very first thing you do in point2.c, well, not the first thing you do, but one of the first things you do is include point2.h. Right. So now the definition of our structure gets included into our source code file, and all of the functions get declared. All we have to do now is define the functions. Right? Remember when you are including your own header files, they're included using double quotes. The less than and greater than, those mean that the header files you're including, those are system level header files. So your compiler knows where to look for anything that's inside of less than and greater than. Right? For your own header files, you put those into double quotes. Typically, they're in the same directory that you're compiling in, but they don't have to be. So there is a way to tell the compiler where to look for these things as well. But that's not important for our purposes right now. Okay, so now you define your functions. Right? So I want to move the point P by dx and dy, right? So I want to add dx to px, and I want to add dy to py, right? Now remember, p is a pointer, so I can dereference and access the member using the arrow operator, right? So p arrow x plus equals dx just adds dx to the x coordinate of p, right? P arrow y plus equals dy just adds dy to the y coordinate of p. Right? Multiplication is similar, right? I'm just going to multiply px and py by s. Right? Equals, I want to compare px to qx, and I want to compare py to qy. Right? So if px and qx are equal, and py and qy are equal, then the 2 points are equal. Otherwise, they're not. Right? This is fine for most purposes. It's not fine if you need to handle not a number. So remember, not a number in C, not a number according to the IEEE floating point standard is not equal to anything, not even itself. So if you're in the situation where you need to handle not a number, you have to write some extra code to deal with it. Right? I'm just going to ignore it for now. And finally, toString. So this slide contains some errors. It's not correct. And so coming from a language like like Python or Java, it's natural that you print stuff out, especially when you're debugging. In C, that's less common because it's not so easy to print stuff out. Right? So in particular, if I wanted to print out a point, right? If you remember how printf works, right? In printf, the caller of printf is able to control how many significant digits get printed for a float. Right? And so here, if I want to print out a point p and its coordinates are doubles, then you really ought to be asking the caller how many digits of significance do you want. But it's actually more complicated than that, because really you should be asking the caller, how do you want this number formatted? And we're not here. And so this becomes a bit complicated to implement functions like toString. Right? So this thing here is supposed to return a string representation of a point, just like you would do toString in Java. Right? So how are we going to do this? So first of all, I need to return a string. A string's just an array. I can't return an array in C, so I have to return a pointer to a car. Right? If I'm going to return a pointer to a car, I have to make sure that it's dynamically allocated. So the first thing I'm going to do is I'm going to allocate enough memory for my string. Right? So I'm going to malloc a value of size buff size. Now buff size is wrong in this case, and I'll explain why in a second. Okay, so if this succeeds, I'm going to use this function called sprintf to print the point into my string. So that's what the S indicates here. Right? Printf prints to standard output. sprintf prints to a string. Right? So sprintf prints to the string that's buff. Right? It takes in a conversion. So here I'm using round bracket %g comma space %g round bracket. Right? So what that's going to try to do is it's going to try to print a round bracket into buff, followed by the x coordinate into buff, followed by a comma and a space, followed by the y coordinate, followed by a round bracket. So I'm going to try to print all of that into my buffer. Buff is short for buffer, which is a common name for a generic for an array in C. Right? So the way it works the exact same way as printf, except you also tell it what string do you want to print into. Right? So %g is going to try to convert p.x, the x coordinate of p, into a floating point string using the g conversion. Right? And then py is going to try to convert, this second %g will try to convert py into a floating point string using the g conversion. Now remember what the g conversion does. Right? It's either going to use %f or %e, scientific notation, depending on the magnitude of px and py. Right? On its own, it always uses a total of 6 digits. Right? So I know there's 6 digits here, and I know there's 6 digits here, but it's a floating point number. Right? So there's 6 digits, right? Plus a decimal point, so that's 7, right? Plus a sign, so that's 8, right? If it's in scientific notation, there's going to be an e, so that's 9, right? Followed by an exponent that could have 3 digits, so that's 12, followed by a sign, so that's 13, right? So each one of those can take up to 13, each one of those G's can take up to 13 characters, right? At most, right? At most. So how many total characters do I need? I need 13. I need 13s, right? There's 1, 2, 3, 4. So that's the plus 4, right? Plus the trailing null terminator, right? So I need 1 more for the null terminator. So that's 13 and 13, so I'm using 15. So I actually have excess capacity in this string. Right? So this actually works okay. Right? N, in this case, is the number of arguments, so px and py, that are successfully converted using %g and %g. Right? So, sorry, not for printf. Sorry, not for sprintf. Sprintf, n is the number of characters that are printed into the string. So in this case, if it's less than 0, there's an error. It didn't print any characters into the string. Right? If it's greater than the buffer size, then I've gone past the end of the string, which is bad. Right? Because because when I return the pointer to that buffer, right, whatever is past the end of the array is not going to be there when the caller tries to use the buffer. So that's also an error. This should never happen, the second condition. Right? If either one of those conditions happen, though, I'm going to free the buffer and return null, which indicates that this thing didn't work. Right? So our function here returns null if it doesn't successfully print into the buffer. There's no good reason it shouldn't print into the buffer, but it's here just for safety. Finally, I can return the string at the end. Right? So notice that even in this little example here, right, where I'm just creating a string from 2 doubles, you've got to write a lot of code in order to do that. Right? In Java, you would just write return round bracket plus px plus comma space plus plus py plus the closing round bracket, right? So string handling in languages like Python and Java is much easier than in C. And we're going to see this again when we talk about lists, right? Generally, if you're trying to convert something to a string, you probably shouldn't be doing it for somebody else. You should let whoever wants to convert it to a string, you should let that be their problem. Because you never know, you don't really know how they want to convert it to a string. Right? There's a big problem here, right? So this always returns a point as though it had only 6 digits in its numbers. There's a lot of cases where you want more digits to come back, right? But the only way to do that is to now ask the caller for the conversion specifiers here. Right? And if you're going to ask the caller for the conversion specifiers, you might as well just let the caller do it themselves. So yeah, it's nice in theory to provide this function, but in practice, the caller is probably going to do it themselves anyway. All right, so that's plenty for today. We'll end it there. Don't forget, you do have a quiz on Wednesday. If you look at the announcement on OnQ, there is a link to last term's quiz. So the quiz for this term has a similar format. Questions are obviously different, but the format is similar.